Thank you. The title of my talk is Ionic Floating Gate Memory as an Artificial Synapse for Neuromorphic Computing. And this is part of a collaboration between Stanford University, University of Massachusetts Amherst, and Sandia Labs. Let's see here. So I'm interested in developing artificial synapses that can be used in arrays that could accelerate the core matrix operations for artificial neural networks. So in that sense, they would be neural network independent, but accelerate the most computationally intensive and energetically costly tasks. And here I'm just showing an example of vector matrix multiplication, but also just as critically important, at least for training, is the outer product update. And the idea basically here is computation and storage is co-located, calculations are executed in parallel and within a single compute cycle. This has the potential to increase energy efficiency and latency by up to 10 to the fifth compared to a traditional CPU, and 10 to the 3 compared to state-of-the-art optimized digital accelerators. But what we really need is a very high-quality synapse or device that can store the analog weights and is very low energy. And we also need this type of synapse to be scalable to large arrays. If you want to make this crossbar generalizable to a variety of algorithms, there's circuit overheads associated with the crossbar. And so it turns out you need arrays that approach 1,000 by 1,000 or even larger in order to actually realize really, really great performance benefits and energy efficiencies. And we also need this element to be linearly programmable if we're going to carry out massively parallel training operations. If you do element-wise training, you can get away with asymmetric behavior, but you lose your accuracy for your matrix operations, and you end up with a phenomenon called state decay. And this is a big problem if you're going to implement nonlinear elements. And so there are challenges with existing memory devices that are used or proposed for crossbars. Existing two-terminal devices, for one, are subject to the so-called time voltage dilemma. And that means that you really need, for at least a two-terminal device where the read and write functions are passed through the same terminals, a large energy barrier for retention. You lower the barrier, you lose memory due to read disturb. And what this ends up leading to is large voltages and currents that are dropped in your crossbar. And these circuit parasitics mean that it's really difficult to scale to large arrays to realize that big bump in energy efficiency. And so this is a major challenge with these types of devices. The other challenge is that they're nonlinear and asymmetric, meaning if you look out in the literature and you look at these types of crossbars, they can be accurate, but the training operations that were carried out on them are all sequential. They've had to element-wise program each of the individual elements in order to achieve high accuracy. And so we've been investigating the idea of a three-terminal device to try and circumvent at least this time voltage dilemma. And so this is not new. Floating gate memories have been proposed as artificial synapses for quite a long time. And there's current ongoing work. For example, excellent work by Dmitry Strukov's group at UCSB recently developed a NOR flash accelerator with high accuracy. But these types of devices have similar problems with RRAM in that they are high voltage and nonlinear elements, the NOR flash cell. And so training is, again, not in parallel, and you have to element-wise program these cells, typically. And so in order to realize memories that can improve upon the floating gate concept, we've been investigating new types of materials that are traditionally not thought of for neuromorphics. I say it's relatively new because there is some work. But so we've been investigating specifically ion insertion electrodes. This would be transition metal oxides or redox active organic polymers. And I don't have time to go into all the physics of how these devices work, but here's some, I put up some papers in case you want to read about them. But the take-home thing here is that they're mixed ionic electronic conductors with oxidation-dependent electronic resistance. And this resistance change is an intrinsic material property. There's no filaments, and ion insertion is inherently low-energy process. So you can program these devices with 100% Coulombic efficiency. They can operate at low currents, and they can even switch. You can even have ion insertion occur at very low voltages, as low as 10 millivolts. They have nonlinear programming regimes, but they also have linear programming regimes. And so we've been exploiting those for use in storing memory. They can hold hundreds of distinct analog states, and also of interest to floating gate memories is there's a high charge density per state per volume, which relaxes strict requirements for leakage. And so we've been implementing these types of materials into transistor type configurations, electrochemical transistor type configurations, specifically Redox transistor. And the device is actually operationally very similar to existing CMOS-based floating gate memories. You have a floating gate, which stores charge, and you have a control gate, which mediates electronic coupling to the floating gate. And so these redox transistors require charge to program in order to transport ions between the channel and gate and modulate the resistance between source and drain electrodes. And in order to retain state, we've been using a control gate of a volatile filamentary switch. This is basically a memristor with no memory. And this is because we've tuned the activation energy very low to be about 10 kT for these devices. They're from the Yang group. And they're normally off, so they prevent charge injection into the floating gate and retain memory state. But they can, because of this low activation energy, they have a very low voltage threshold for turn on. And so in very low voltages, we can actually form this filament, inject charge into the floating gate, and program the device. And because, again, of this low activation energy, this filament quickly dissolves. It's been shown to occur on hundreds of nanoseconds time scale into the off state, preserving the conductance state of the device. And in this way, we're able to take this linear element, this redox transistor, and combine it with this nonlinear selector to achieve linear type programming at low voltages. Here in blue, I'm showing programming at 1 volt, and in black, I'm showing it programming at 650 millivolts. These devices will program at a minimum, we've found with these particular thresholding devices, of about 400 millivolts. But we are looking to lower that voltage. You compare this to a traditional CMOS-based floating gate memory. You can try to lower the range to improve the linearity and asymmetry, but you'll never get there completely because of the exponential sensitivity of Fowler-Nordheim tunneling on the floating gate voltage. In our particular device, we're only linearly sensitive to the floating gate voltage. And we've also been able to demonstrate accurate outer product updates in a small prototype array, a very small 1x2, but it illustrates the concept. By the rules of the outer product update, we can linearly and accurately program and each device without disturb in the array. And so if you were able to generalize this to larger networks, which we're looking to do, you could support massively parallel training operations. And since training is one of the most computationally intensive tasks for neural network algorithms, this is a very exciting result for us. We're also able to achieve, more recently, we've been able to demonstrate the low read currents that are needed for these large crossbar arrays, below 10 nanoamps. And you sort of get this for free when you go to 3 terminals because you can just simply achieve this through doping. But we've been able to preserve the signal-to-noise ratio as well as a lot of the linearity, even through doping some of these devices. We've demonstrated endurance of our redox cells of 1 million cycles. We haven't had one fail yet. The diffusive memristors have shown endurance at 10 to the 8. It's not good enough. Actually, you need 10 to the 13 for the lifetime for these things to be useful, but it's a work in progress. So we're working on that. So just to summarize, we've developed a floating gate memory that can switch at low voltages and currents, is capable of linear weight updates, and hopefully therefore scalable to large arrays. It's capable of accurate outer product update to support massively parallel training operations. I apologize I didn't get to go into a lot of the physics and chemistry and actual challenges associated with building this type of memory. But please come see me at my poster and we can talk about all of that. Yeah, and I'd like to thank the Soleo group at Stanford as well as the Yang group at University of Massachusetts Amherst. They fabricated a lot of these materials and devices for us, and it's really been at Sandia where we put them together and put a lot of these ideas together. Thank you.
Thank you very much. Are there questions? Yes, please.
First of all, nice work. So I was wondering, you mentioned low voltages, but I saw that you also need to use very long pulses, so compared with the memristor approach. So is this the fundamental limitation, or is it possible to make these pulses shorter?
It was a long pulse, you're saying? Sorry?
The long pulse time.
Long pulse time, that's right. No, so that's not fundamental. That's simply due to the fact that these devices aren't scaled yet. And it's actually the Redox transistor device that's limiting that, because right now we're working with planar devices. So there's just simply the ion diffusion times are killing us as far as programming speed. But that's simply that limitation. So one of the first things we're looking to demonstrate, actually, and most important things, is speed and scaling in order to, because we know we're going to need it. But with that very good observation, I didn't get to that, so thank you.
So what kind of pulse times are you looking at for scaled devices?
For scaled devices, we're looking at, so for this particular material, which I mentioned, P.PSS, it's actually a supercapacitor. So you're limited by the proton transit time through the electrolyte and through the material, which is about 150 nanoseconds. But it's a complex equation, it turns out, between retention, charge density, and these other phenomena. So we'll see what we run into, but I think something like a megahertz is probably maybe a little bit better.
Okay.
But we're hoping through massive parallelism, we won't necessarily need to reach gigahertz speeds with these devices.
Okay, thank you. I will come check out your poster.
Sure.
One more.
All right, so you have shown coupling the selector with your three-terminal device and then the voltage programming.
That's correct, yeah.
Yes. Could you confirm what is the material stack? Is that a lithium stack? And for the voltage, did you use constant overdrive or constant voltage? Because that's a
So this is constant
difference.
voltage. This is just to the drain 0 volts plus 650 millivolts. That's one of the programming curves I showed. This is not a lithium device. We have lithium devices that we're investigating. They are capable of lower voltage operation due to certain physical mechanisms in the floating gate voltage which you accrue. So yeah, we're working on that. They're a little more difficult to fabricate than the plastic polymer devices that we're actually using. Although the plastic polymer devices are very interesting.
So that was your proton-based device?
That's the proton-based device,
good,
right.
Thank you.
There are different scaling considerations for lithium devices, but yeah.
Okay, thanks again for your talk and the discussion.